Welcome, chemistry students, medicinal chemistry. It is March the 18th today, and I am looking at your packet, and I want to talk to you about questions number 4 and number 5. I'm going to give you an example of how to work through those problems. I've just sat here and worked through them for an example for you, so I will touch on that. But first, I want you to look at your chapter 14. And I want to give a shout out to Cam. He did an excellent job on making a chart for chapter 13. And so if you listen to Monday's lecture, I was giving you an example of how to make the functional group changes and why, the strategy. It's very important that you do this chart, and because if we do come together for a face-to-face course final, I'm going to allow you to use your charts. Okay, so take the time to do that, and it will also help you if you have a timed exam. So chapter 14, I want you to do the same kind of chart. So first of all, let's learn a few of the concepts. Let's learn, and then also do the chart. So one of the important things here is on page 256, what is the hydrophobic characterization of a drug? Hydrophobic character of a drug can be evaluated with a thing called log P. Okay, we've talked about log P a little bit, but this is where the hydrophobic character of the drug can be measured experimentally. And so what a chemist would do is take a separatory funnel, and they put water, and they put in octanol. And that is 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8. And this mixture, and this kind of represents our cells' lipid bilayer. And we put our drug molecule in there, and then you can measure how much of that drug, the amount of that drug, is in the octanol layer. And so the formula becomes P equals the concentration of the drug in the octanol over the concentration of the drug in the water, the aqueous. And so if it has a high log P value, this would be hydrophobic. So many drugs exist in the equilibrium between ionized and unionized. So log P actually measures the relative distribution of an unionized versus unionized. So this would be unionized. If it's in the octanol, and it'll be ionized, meaning it has a plus charge, usually your amines, versus formal charge is 0 if it's in the water. The relative distribution is given by log D, so you can read this. But basically, hydrophilic compounds have a low p-value. Hydrophobic compounds have a high p-value. So if you have a high p-value, it's typically hydrophobic, and if you have a low p-value, it's hydrophilic. And that's going to be important. We're going to make changes to these drug molecules, and this is the chart I need you to write. So in this chart, this new chart, and I want you to do this for all of chapter 14. So I'll get you started, and then you can finish the chart. Okay, I want you to do your strategy. Okay, and then I want you to give an example. And so when I look at here, I look at the first one is the first strategy that you can make changes is you're going to mask the polar functional group. Okay, so if you want to decrease polarity, that's a strategy. Then you can replace it with alkyl groups or ester groups. Okay, if you wanted to decrease a phenol, then you can make an ether. If you wanted to decrease a ester, a carboxylic acid, then you can make an ester. Trying to make sure that my internet connection is not lost here. Okay, another strategy too, if you look on page 257, you can add or remove polar functional groups to vary the polarity. And so an example is the OH group or a polar aromatic or heterocyclic ring. So these, if you added these onto a molecule, that would increase your polarity. And then you could remove any such groups to decrease your polarity. And this polarity, this is like water soluble. This thing called the methylene shuffle. Okay, this is when you modify the hydrophobicity of a compound. So you can add halogens, so chlorine or fluorine. Bromine is less common, but fluorine or chlorine, this will increase your hydrophobicity. So the halogens actually increase your hydrophobicity. Okay, so what is another group you could do? Another strategy, you can vary your N-alkyl substituents to vary your pKa value. So if you look at this, I'm on page 258 now, and I'm looking at the strategies. And so most of your drugs, your goal is to have a pKa range between 6 and 9. And remember the means, where they get protonated. Okay, that makes them more water soluble. And so your different acids and bases have this quality trait, your acidic proteins versus your basic proteins. Also aromatic substituents. If you put electron withdrawing groups or electron donating groups, you can vary the pKa values that way. You can also make changes for, so I'm on page 258, the bioisosteres. Do you remember what bioisosteres were? They basically mimic the electronic and physical properties of a functional group. And so for a carboxylic acid, a mimic could be a tetrazole. And so this would be considered a bioisostere of carboxylic acids. A hydrogen, if you wanted to block a hydrogen, a bioisostere is a fluorine. NH groups, a bioisostere would be an OH group. So these are ways to change those bioisosteres. Okay, you can continue on with your chapter and And the first thing I'd like for you to do is to go ahead through chapter 14 and do just as I am doing and make a chart, a really nice chart for yourself, and make those changes. And then what I would like for you to do after you do that is I want you to work problems 4 and 5 in your handout. Number 4 asks you to make structural changes. And I have done this exercise, and I will post this onto Canvas because you can't see it. But what I did was I went to molinspiration. So I went, and I would love it if you would do this with me, if you can. Molinspiration.com, and it's a free software, and it's on number 5. And so if you go there, you'll see where you can draw molecules. Now, you'll see a thing that says enter smiles. And if you actually enter that, that would actually pull up your structure. And you've seen the smiles in your drug bank. You've probably seen that. You could literally copy and paste that into this enter smiles, and it will pull up your drawn molecule. Or you could draw your molecule. Now, when you draw your molecule, which I drew my molecule, there's a smiley face. I guess that's for the smiles, actually. And then there's this white thing here, and there's no space here, and then there's a red X. Okay? Let me tell you, you're going to do this, but don't do it. Do not hit that. Because when you hit that, it clears your entire board. Okay? So when you're making these changes, because if you read questions 4 and 5, you have to make 6 changes to the molecule. So you're going to pick a molecule, a lead molecule, and I'm going to take you through mine, and I want you to do it. Put in a lead molecule, and then you're going to make 6 changes. And you're going to have to write down what your strategy was. Now, I am going to have a Word document, and I just copy and paste the picture. So I like to take a screenshot, and then I put that in the Paint program, and then I put it in a Word document. And that's how I've uploaded mine. But the first structure, before you get started as well, when you predict the bioactivity, click on that and read about that. It talks about drug likeness and bioactivity series and what those numbers mean. There's 6 targets. So of those 6 targets, those are the targets I want you to choose from when you're figuring out yours therapeutic area. Because these are the 6 targets we can measure structural changes because we have this tool called molinspiration. Now I chose nuclear receptor ligand. And I've got a nice review article that I will post along with this video on a nuclear receptor ligands. And these are basically molecules that bind enzymes, and those enzymes then bind conserved places on the nucleus, inside the nucleus, and on the DNA. And on that DNA, it causes transcription. So genes can get turned on or off, okay? And that's why they're nuclear receptor ligands. So I'm targeting DNA as my receptor target. And so I chose nuclear receptor ligand. And you'll see the first one, so you can put this in OC3, CCC, 2N, CC, C1. That's my smiles, okay? And like I said, I'm going to put this all available for you so you can see how I want yours done. Or you could draw this molecule. So I drew this molecule in. Oh, don't put that one in. That's not there yet. Here, put this one in. So this is the one I put in. I put in this structure as my starting. Okay, so this was my starting molecule. So draw that in. Okay, and then I hit the predict bioavailability. And my nuclear receptor ligand gave me a score of negative 0.46. That's not very good. The goal is to get a positive. We want more positive, large number. And a winner will actually come back in green on this molinspiration. So your goal is to start with a compound, a lead compound, and then make structural changes. So we talked about some of these structural changes. I decided that I wanted to increase my polarity. And so if I go to these strategies that we were writing out earlier, I can do this by removing a Cl group. And I also decided to go ahead and add an NH group and an OH group on the ring. So I went ahead and I drew this structure. So you can draw this structure in there. So you can see that I kept this ring here, and I decided to replace this Cl with a nitrogen, and then I wanted to tie this back here. So I did a tie back. So I restricted rotation. So I want you to kind of monitor what changes you're making, and then I added this OH group. So I added 2 polar groups, and then I hit the predictability, and it came back a score of positive 0.1. Okay, so I thought, wow, okay, that's a pretty good jump, right? We went from negative 4.6 all the way to positive 0.1. Now keep in mind, I want you to do about 6 changes. It doesn't mean they're always going to be in the positive. So the next change I decided to do was to walk this OH around the ring. Okay, so I'm going to put it here, and then I'm going to get my score there, and then I'm going to put it here and get my score, and then I'm going to put it here and get my score. And so if you look, I did that, and I walked it all the way around the ring. I think I only put 1 on there. Yeah, I only put 1, but I did walk it all the way to the ring. You can put all 3 of yours. And that was my strategy, was to find the OH. This would be a hydrogen bonder within the receptor. Okay, so I wanted to find if I had the right location. And you know what? It went down. I got a plus 0.1. Okay, so it went down. I think one of them even went negative. Okay, yeah, it went like to negative 0.46 again. So what I posted on there was a positive 0.1 and saying, you know what, this is not going anywhere. So the next thing I decided to do was introduce a hydrogen bonder on this ring here. So then I put in this structure, and I would like for you just to go through this exercise with me. So I went through and I drew this structure. I put an OH here, and keep in mind I kept my OH here. And what do you know? I got a nuclear receptor ligand of plus 0.24, and I put it in green because they put it in green, and that would be a winner. Okay, so if you look at your pages, this is what you're supposed to do. You're supposed to take your lead compound, pick one of these receptors so we can trace it, draw your structure, put it into your molinspiration, and then you iterate what changes you're making, why you're making that. And that's where that chart strategy is going to help you if you take chapter 14 and put that in the chart. Okay? So that is your homework. And you also have a quiz. So will have that posted obviously in the morning, so you have that quiz to turn in and work and turn in. And then we'll revisit any kind of questions you might have on this on Monday. Have a good weekend.